Welcome to Brain Vision.
So in normal operations, the capacitor is fully charged by the power supply, and therefore the capacitor voltage will be equal to the power supply voltage. So this is for the case of normal operation. Now, if there is an interruption, the capacitor voltage, which is V, so this will decrease exponentially and it will discharge. So the equation for the capacitor voltage then will be V naught e to the power minus T over tau, and tau here for an RC circuit is R times C. Now we want the voltage across the capacitor to be 75% of the full voltage, and we want this case after 0.20 seconds. So V is 75% of V naught, which is 0.75 times V naught, and this occurs after t equal to 0.20 seconds. So let's plug these two over here. So we have 0.75 times V naught equal to V naught e to the power minus 0.2 seconds over RC. V naught is a constant and that cancels out. So we are left with 0.75 equal to e to the power minus 0.2 seconds over RC. And from here, we can solve for R, which will be equal to 0.2 seconds over C ln of 0.75. And C, the capacitance, I think I'm a little bit lagging here. So C is equal to 8.5 times 10 to the power minus 6 Faraday. We plug these value over here, solve it for R, the resistance, and we find that to be 81790 ohms. Now, a little bit simpler method with respect to the calculations could be first, since you already know what you need to find, which is R here. So first, it's better to express R algebraically, solve this equation to express R, and then plug the values of each, like time and voltage and capacitance, of course, to solve for R. That way, you won't need to care about the values. The values could be a little bit confusing. Like over here, I have 0.2 seconds. Instead that I could have just wrote t here, and instead of this 0.75, I could have wrote v over v naught. So yeah, this makes your visualization for the problem a lot more easy, and you won't mess up while doing the calculations. So it's always better to express your answer algebraically first, and then plug the values to find the numeric answer. So coming to the second part, when the power supply is functioning normally, there is no voltage across the capacitor. So the device should not be connected between terminals A and B. If the power supply is not functioning normally, then there will be a larger voltage across the capacitor than across the capacitor resistor combination, since some current might be present. Now this current would result in a voltage drop across the resistor, To have the highest voltage in case of a power supply failure, the device must be connected between terminals B to C. So this is the case when functioning normally, and this is when not functioning normally.